Last time we were talking about the Maxwell relations, or relationships, depending on which way you want to look at it. And what were we looking for? We were questioning a partial derivative. What was that partial derivative? Mm-hmm. Yep, S over V holding what constant? Yeah. We wanted to get a way to solve for this because as we go forward, we're going to find kind of crazy derivatives like that. Is this thing easy to measure? No. Like looking at it, what does that really even mean? It's kind of confusing in itself. So a lot of times in thermodynamics and eventually quantum, which only 3 of you get to take, lucky you, you'll run into weird derivatives like this, and you need to find ways to change it to something that's more useful or easy to measure. So that's our goal. We're trying to figure that bit out. Okay, last time though, we had to review something in our mathematical toolbox. What did we review last time? Yeah, exact differentials. So if we do, let's just write it out real quick so we remember what it was. If we had, did we do big F or little f? Let's do, yeah, big F. F it. We had that. If we wanted to look at the change in F, how do we do that? Yep. 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 So basically, we're changing x in this portion, and we change y in this portion. Okay. Now, to show that this is an exact differential, we have to find a relationship between these two things. Oops. Y. And what do we have to do here? This isn't exactly true right now, right? What do we got to do? Yeah. Yeah, with the other variable, what are we going to hold constant in that case? Yep. And then what do we take in the differential on this side? Yep, hold them what constant? Yeah. Okay. Exact differentials are interesting mathematically. Next semester, we'll see situations where there's a lot of times where that isn't true. And the order of things matters a lot, which is weird. What does this tell us in thermodynamics, though? Yeah, state or a path function. And what do we always hope for? Yeah, because it's always way easier, right? Okay. Last time we showed that temperature is what type of function? Yeah, state, which is good because we change a lot of things around. However, our goal was to try and find something like this. So can we find a better expression for that? That's what we're going to try to do today. And then we're going to apply this differential to an ideal gas. Okay, so let's look at the natural variable equations. And we're going to really consider enthalpy. What are the natural variables again? Did you say volume, Lily? Yeah, volume. What else? Yeah, pressure, entropy, moles, one more. Yeah. Yep, so we got to define it that way. You do not have to have these memorized. I really hate memorization, but does anybody know what DH is in terms of natural variables? Yep, plus what was it? Yep. Okay. We also know another way to express this guy. What else is DH equal to? Yep, that is one, but that's not the one I wanted. I want a different one. What? Oh, what was that? That is another way to do it. I don't want that one. Partial. Yep. Holding what constant? Yep. Yep. Plus another partial thing. What's going in here? Yep. Holding what? Yep. I know. It's beautiful and terrible at the same time that you guys know all these different equations that connect to one another. I'm sure you feel the same way when you have to do it on a Quizlet or a daily problem. Okay. Looking at this, we can find expressions, what these expressions are equal to. What are they equal to? Yeah. This one's T. That one's V. So now the physical chemistry, thermodynamics, ACS expects you to memorize all of these things. I hate memorization. I can't do it that way. Like you remember those 8 that we talked about last time? I can't do that. I have to go through this way. So as long as you can do this, you're in a good spot. Okay? All right. What do we know about enthalpy or DH? We know a lot about DH. Let's start talking about it. What do you know about DH? Give me something. Let's start at the basics. Yeah, that's what we want. It's a state function. So H is a state function. If H is a state function, what do we know about DH? What should it have? Exactly. That'd make Professor Snyder way too happy. Has an exact differential. Yeah. No, I had it right. It's got an E here. Right? Yeah. Shannon's shaking her head, looking sad at me. All right. Okay. Now, let's look at that exact differential. So really, we have to consider these two things, right? H, what was it? S, P. What was the other one? H with P. Hold in what constant here? Yep. So to make this true, what do we have to differentiate with respect to on the left side? Yep. And what are we holding constant? Yep. For the right side? Yep. Okay. Let's investigate this side first. Ugh. Is there any way we can make this more solvable or easier to solve? I see a couple of head nods, yes. What do you suggest we do? Yeah. What gives us the right to do that? Yeah, this thing here. So we get partial t with respect to what? Because what's this thing equal to? Yep, that's now just t. So what does this all become? Yep. Holding what constant? Yep. Okay, we can look at the other one. If I do it down here, can people see it? Yeah. Partial S pressure. Is that one easier to solve? Or what would you suggest to do to make it easier to solve? Yep, this is volume, so we'll substitute that in. Okay. So how does that help us? What can we do with these two things? Or what has to be true given that h is a state function, it has an exact differential? Yeah, they're equal to one another. Partial Which one of these is easier to solve for? Yeah, this one's way easier. You think about it in terms of the ideal gas law, you just have to manipulate this to solve for P. What about this side? Way more complicated to figure that guy out. Okay, so this is one of the Maxwell relations. And you can show, following the same sort of procedure, looking through the natural variable equations. Actually, I'll do it down here. That. So you can go through the same procedure we just did. and get all of these relationships. All of these are known as the Maxwell relationships. There's a lot of deep connection there that in this class we'll use it a handful of times, but in a lot of other areas it's deeply influential. It makes things way easier to solve. If I said prove one of these, which you'll have to do on the next daily problem, do you feel like you could do it? So you'll have to look at the natural variable equations. You'll have to look at these differentials, and utilizing the knowledge that you have about exact differentials and state functions, you'll have to derive these relationships. Yes, it should be, because that doesn't make any sense. Oh, no, it is V. I'm going to double check that one. I don't like it and trust it. I don't know how that can be true. I think it has to be. Yeah. Yeah, I think it's the one we just proved. Otherwise, that doesn't make sense. And there should only be 4 of them. Good catch. Gotta change that. Okay. Let's apply this. Any other questions about this one? No? Okay. Let's apply this to an ideal gas. Am I okay to erase this side? Okay. So to show its utility, we're going to ask, what is partial of entropy with respect to volume, holding temperature constant, for an ideal gas? Okay, what do you suggest we do first? Given the words ideal gas, what do you think we're going to need? Yeah, ideal gas law. Yeah. Bit of nerd. Okay. What do you suggest now? Do you like this differential? No, it sucks. Can we change that to something else? Can you say that it's P? Yep. Which one are we using? That guy. Okay. So these are true. How are we going to apply that to the ideal gas? Yeah. Solve for P. Then what are we going to do with that? Yeah, plug it in here. Oops. if I take the derivative with respect to temperature, what does this become? Yeah. And that's also equal to this. So a lot of times you can use these tricks, these relationships, to move your differential to something that's way easier to solve. Does that make sense? Okay. Any questions about that? So I should be able to give you any one of these relationships and ask you to apply it to an ideal gas. Okay? Might be one that's way harder than the others. Let's look. No, not really. Any questions about that one? Wherever you have constant entropy, do you see entropy in this equation of state? No, so it's kind of nice. You really don't have to worry about it. Okay. Any other questions? Okay. We're going to